Jess,
Do you have any announcements?
let's get started.
Okay, I guess I got to stand in front of the camera for a second here. Okay, so welcome everybody to the Geosciences Colloquium. I'm Andy Cohen, faculty member in the department, and it's a great pleasure to introduce today's speaker, Dr. and Professor Jess Tierney of our department. Jess received her BA, MS, and PhD from Brown University, and after that she moved to a postdoc position at Lamont Doherty and became a research scientist then at Woods Hole before joining our faculty in 2015. Jess is an extraordinarily accomplished scientist working on the interface between paleoclimatology, climatology, and organic geochemistry. She brings a rigorous quantitative approach to addressing important problems in paleoclimatology and has had an exceptional eye for identifying and attacking key questions with broad academic and societal interests. Her work has involved such topics as better constraining our understanding of global climate during the last glacial maximum, something that I'm particularly interested in, the reconstruction of African climates during the late Quaternary, which is how we came to be acquainted many years ago, and especially using paleoclimate records of past warm periods in Earth history, such as the Pliocene, the Paleocene, Eocene thermal maximum, to better contextualize our future warming planet. Jess's exceptional research productivity has led to many awards, including AGU's James McElwain Outstanding Early Career Award, the Peter Schenck Award in Organic Geochemistry, and the prestigious Packard Fellowship in Science and Engineering. Her accomplishments in working to better integrate paleoclimatology into our ongoing understanding about the direction of modern global climate change led to her selection as a lead author on the Intergovernmental Panel on Climate Change Sixth Assessment Report, Working Group 1, which is going to be the subject of her talk today. Jess, thank you for talking.
Thanks, Andy. It's a nice introduction. Incidentally, Andy was a co-author on one of my chapters in my dissertation. So we did two, sorry. Two chapters in my dissertation. So we go back a long way. Okay, so, but today I'm not really going to talk very much about my own research. What I wanted to talk to you guys about was the IPCC. And so I'll tell you a little bit about sort of like the structure of the IPCC and how this works, you know, how it's sort of structured, the report is structured. And then I'll go over some of the key messages and we'll see how the time goes. But, you know, my plan was to end a little bit early and potentially allow for more Q&A, because I know a lot of people have a lot of questions about the report, how it was put together, and also what are some of the impacts of the report that have come out since it came out in August. Hopefully I can, there we go. Okay, so first of all, what are the IPCC assessment reports? What are these things? So this is a report that assesses the science of climate change, and there's essentially three parts to it. The Working Group 1 report, which is what I helped author, is the physical science basis. Working Group 2 is adaptation and vulnerability. So we're bringing in sort of a social science view with that one. And Working Group 3 is mitigation. So how do we take down emissions? How do we combat climate change? Actually, the Working Group 1 report has just come out in August, and that's what you've seen in the media. The Working Group 2 and 3 reports are not yet out. They will actually be coming out next year in 2022. And so we get a lot of confusion about that because people ask us, well, what about adaptation? What about mitigation? We have to say, that's 2 and 3, so stay tuned. Not coming yet. This is just a timeline of the report, sort of the reports through time. So the IPCC was established in 1988, and then this shows you the spacing of the reports over time. And so it basically, the first report was in 1990, so shortly after the IPCC was founded. So first assessment report, or FAR for short. Then we go 5 years to the SAR, the second assessment report. In 1997, the Kyoto Protocol was adopted, but didn't go into force later. And the underlying, sort of agreement of the Kyoto Protocol, which the US did not take part in, was to hold global warming to 2 degrees Celsius. We moved to 2001 with the third assessment report. And so you can see that they're spaced about every 6 years. That was the typical spacing of these reports. Kyoto goes into force in 2005, and 07 is the AR4, the fourth assessment. And that's also when the IPCC won the Nobel Peace Prize for their efforts in assessing climate change. Fast forward 2013 was the last round, and now here we are 8 years later now with the sixth assessment cycle. In between, however, some important things happened. Paris Agreement is in 2015, and in the Paris Agreement, small island nations expressed concern that 2 degrees Celsius was too much. Our nations will be underwater. We need to hold to 1.5. And coming out of the Paris Agreement was also an agreement by the IPCC to do a special report called Special Report on 1.5 degrees warming, which came out in 2018. So there was an interim report that came out specifically about assessing warming at the lowest, essentially the lowest global warming level that we could achieve. So that's a little bit of the timeline, sort of the history behind it. So how does one become an author on the IPCC? People ask me this question, so I just wanted to explain. Basically, every country will nominate a set of scientists to serve as authors on the report. And so each country will have different policies. In the US, organizations like GSA, in my case, Pages Network, which is actually European, but nominated me as a potential author. And so you can basically, they field nominations from anyone, nominate scientists to participate. The US Global Change Office, we do have a Global Change Office. It was hiding for most of the Trump administration, but it's a very nice people work there. Ultimately selects the author team for the United States. The position is about 3 years long and it's unpaid, which I think you guys know, but a lot of the public is astounded to learn that we actually don't get paid or really compensated, except for travel is covered by the governments in any way. So the statistics for Working Group 1 this time around was that there's 234 authors from 65 countries. So about 22 of that, so about 10% from the United States. The dominant author pools from Europe, European countries. You can see that the gender statistics are not awesome. 28% women and 3/4 men, and they've only been worse in the past. So improving very, very slowly, but pretty far from gender parity. This round, 30% of the authors were brand new to the IPCC. That includes myself, first time that I participated in this process. So what's the structure of the report? You see this thing come out, there's different parts, and you're probably wondering, like, what are all these different parts? So I just want to break it down, like, what are these parts? So basically, the meat of the report is the chapters. There's 12 chapters in the Working Group 1 report. The chapter I worked on was water cycle changes, and we have these different tiers of sort of authorship and responsibilities for the chapters. So first of all, you have the coordinating lead authors. These are basically, the buck stops with them. They're responsible for getting the chapter delivered. They're the coordinators. Then you have the lead authors. So you can see the lead author list there. That includes myself. And the lead authors are basically writing the thing. So we're doing the writing, but we may actually go and ask some of our colleagues out to say, hey, can you contribute a paragraph on this topic, or can you help me with a figure? And for that, we go to this long list of contributing authors. So people that helped us out with the writing or the images, the figures, and so are acknowledged for their contribution, but they're not actually part of the IPCC official author team. And then we have the review editors. Those are like internal reviewers that are a part of the chapter team, look through basically what we write and critique it, make sure we haven't missed anything. Finally, the chapter scientists are folks who are helping us with the data and some of the figure making, especially making figures of the future projections, pulling that from the ESGF database and making nice plots and things like that. So you can see it is a team effort. Each chapter is about a little over 200 pages long, so it's a lot of text, and it's a lot of work. I should also mention that the IPCC text goes through several rounds of open public peer review. Anyone can comment on the drafts, the first and the second draft of the IPCC. We receive thousands of comments and we have to respond to every single one in a in an Excel worksheet. And even if the response is, yeah, no, I'm not going to do that, you have to respond. So there's a lot of accountability. So addressing the comments is a lot of work as well. You can imagine. Some people are useful and others, you know, maybe not, right? Okay. There we go. So the full report, those 12 chapters that I mentioned, plus the atlas, which I'll mention in a second, is over 2,000 pages long. So most people aren't going to read that, right? Like you can't sit down and read that, and nor do we really expect you to. But it provides an excruciating detail on tons of different issues on regional level climate change. And so because the report is so extensive, there are these summary products that are put together, which is more likely what you would be reading. So the first level up is the technical summary, which is a relatively small 150 pages. And the technical summary, just like its name said, is designed to be a summary for scientific, written for scientists. So understandable to us in the room, more or less. But that is still too long, obviously, for policymaking. Hence, the summary for policymakers is the product that most government officials, politicians will be reading. They probably won't still read the whole thing, but it's 40 pages long. So the summary for policymakers, or SPM, is probably what you'll download and read first, right? And then, but if you want to go back and learn more detail about, let's say, your specific region and what the projections are, the summary for policymakers and the technical summary have links back to the chapters. So you can kind of go back to the base level and find the information that you want within the 2,000 page long report. I don't know why this is turned on, but all right. So the IPCC report is not a venue for new science, and it's not a review paper. It is an assessment, which is something different. So I want to explain what that is. So an assessment, it's designed to collate all these papers. And there's like 14,000 scientific publications were assessed in the Working Group 1 report. So it's a lot of papers. And put them together and assign some level of confidence for like, how well do we know stuff? So how well do we know that there's an observed trend in precipitation in this region? How well do we know, what's our confidence that moving forward, drought will increase in this place? So that's the main point of the assessment, is to actually synthesize stuff, but in a way that has sort of an angle towards policy relevant phrasing. So in the game of assessment, there's two sort of assessment scales that the IPCC uses, and you'll see this language in the summary for policymakers in the main report, which is the confidence scale and the likelihood scale. So the confidence scale is here on your left-hand side, and it's a qualitative scale. Okay, so this is based on theory, data, knowledge, expert judgment, rooted in the literature, but can be any of those pieces of information. And the confidence scale goes from low confidence, medium confidence, up to high confidence. And so what this is sort of telling you is there's kind of like sort of two dimensions to this. On the x-axis, we have the amount of evidence, the type of evidence, the quality, consistency, when you look across a lot of papers. The y-axis, how much of the studies agree? So you could say, for example, you have a lot of studies on some subject, but they completely disagree about what's happening. So that would still be low confidence, even though you've got quite a bit of evidence. Conversely, you can have a case where there's not too many studies, but you actually, they all sort of say a similar thing. So you are kind of up in this corner. Ideally, the highest confidence is over here in this upper right-hand corner, where you have a lot of studies and they're all sort of coming together to say the same thing. So you'll see this use of low, medium, and high confidence, and that's what it is. It's qualitative, which means it's subject to human bias. So absolutely, chapter authors disagree about assigning confidence to things. And we would have very long conversations over Zoom about assigning confidence to certain things. Because it is a qualitative scale, and one person's medium confidence may be somebody else's high, and so on. Now, and on the other hand, the likelihood scale, which is on the right-hand side here, and I'm kind of in the way of it, so I'll move here. This is quantitative. So this has to be based on a probabilistic statistical assessment. And so you can see that these terms, which include everything from exceptionally unlikely to virtually certain, have a confidence associated with it, a probability, right? So virtually certain means 99 or greater % probability. Very likely, what you see a lot is the 90 to 100% range. Likely is essentially your 1 sigma, right? About as likely as not, 50-50. Okay, so this has to be based on statistical analyses. So it's quantitative now of either observations or models. So you see this scale used a lot in the future projections because we can look at all the ensembles of the model runs and assign a statistical probability of a trend emerging in some region, for example. So that's that scale, and that's the scale. So 2 types of scales. So I'll just give you some examples of where this scale is used. So one example, the confidence scale is often used for observed changes where maybe there isn't enough data to do a probabilistic analysis, like a proper full probabilistic analysis, so you need to rely on the confidence scale. So what we're looking at here is a figure from the summary for policymakers, and it's these are these regional hexagons that the IPCC has sort of divided up the world into these different regional areas, and so it's kind of a cool like visualization of the world where every hexagon is the same size. And if this is particularly for observed changes in agricultural ecological drought, which are 2 more specific types of drought, but pretty much the common types of drought. And so the hexagon is colored if there's been an observed trend. So one level of the assessment is, has there been a trend? Yes or no? So you can see that there's some trends popping up, like where we are in Europe and the Mediterranean and South Africa, of an increase in drought. There's a decrease in drought in Northern Australia. And then the dots are the confidence in the human contribution to that trend. 1 dot means low confidence, 2 means medium confidence, and 3 means high confidence. So there's a confidence scale in action. You'll notice that Western North America has 2 dots, and is denoted here as medium confidence. However, our chapter begs to differ. We assess Western North America as high confidence. So there's actually differences even within the report. But that's okay. Either way, we say, you know what, we have fairly good confidence that there's a human influence on drought here in the Western US is the way to read it as a policymaker. You can argue over medium or high, but we have confidence in it. It's not low. So in contrast, if we take a look at an example of the likelihood scale, so again, this needs to be based on data. So one example of where this is used in is the assessment of equilibrium climate sensitivity, which is a metric that's defined as the amount of global warming that comes from doubling CO2. So it really comes from the modeling world, where you run a model, you double CO2, let it come to equilibrium, measure how much temperature change has occurred, and that's your ECS. So this is an emergent property in models, but we can also estimate ECS from data. We can estimate it from the historical record of temperature change, and we can estimate it from paleoclimate as well, past climates, where if we know CO2 change and temperature change, we can calculate it. And so in chapter 7, they present all these different sources of evidence of constraints on equilibrium climate sensitivity. The bigger the number, the more sensitive the planet is to CO2. That's why this is an important metric. And you can see that they've got these different distributions that correspond to the very likely range, which is a 90% confidence interval, the likely range, which is essentially the 1 sigma, and the extremely likely, which is that 99% confidence, right? So you can see how those are used there. And the takeaway, from this particular exercise is that the very likely range or limit of ECS, according to this assessment, is between 2 and 5 degrees Celsius. which by the way is a little different from the last round where it was 1.5 to 4.5. So it's shifted up a little bit. How is paleoclimate used? You just saw there that paleoclimate was coming into the ECS estimate. So how does the geological record of climate change get incorporated into the report? In the past, there had been a chapter dedicated to paleoclimate, a literal paleoclimate chapter. For this report, they changed it up. It is integrated into all the chapters where appropriate. So this is kind of nice in a way because the geological evidence is used where it can provide extra constraints on either what has happened or what will happen. So just as in it, you saw that it came into the ECS estimate because we can use past climates like the Ice Age, the Pliocene to add into ECS. And this is another example of a figure from our chapter that I made that actually uses the Younger Dryas event, this cooling event that occurred 12,000 years ago in response to a shutdown of Atlantic meridional overturning circulation, or AMOC for short, MOC, and compares it to a hypothetical collapse of AMOC under doubled CO2. So a topic of much discussion and part of the assessment in the report is what is the probability of a collapse in the Atlantic meridional overturning circulation, which you may also know as the thermohaline circulation, the formation of deep water in the North Atlantic. Now, it turns out that the probability of a collapse is very low, as assessed by the AR6 report, but it's not something you can rule out. And so we call that a low likelihood, high impact event. And those have specific storylines in the reports. And so one of the storylines that we wrote about it was, hey, we know that during the Younger Dryas, 12,000 years ago, that AMOC did shut down or at least slow down very significantly. And this is a model simulation in the back of what happens to the hydrological cycle. It basically gets drier in the northern tropics and wetter in the southern tropics. All those dots are geological evidence for drying or wettening, during the Younger Dryas event. And you can see that generally the geology and the model are telling the same story about regions that are drying, the northern tropics in Europe, for example, and Asia. Then when we switch and move to an example where this is an induced AMOS collapse, incidentally with the same climate model, under a doubling CO2. So raising CO2 does have a tendency to weaken the Atlantic overturning circulation. And in fact, the projection of the IPCC has pretty high confidence that the AMOC will weaken in the future, but very low confidence that it will completely collapse. But this is just showing you what would happen if it did. And you can see that it looks kind of similar to the Younger Dryas, with the southern hemisphere tropics getting wetter and the northern hemisphere tropics drier, and Europe drier and Asia drier. So it's sort of to show a symmetry between something we know about from the paleoclimate record and something that could happen, albeit a low likelihood but high impact event. So that's just an example, but paleoclimate is really throughout the report, which is kind of cool. Okay, so one of the big parts of the IPCC, of course, is charting our path in the future. And so I want to explain what these pathways are and kind of what they mean. So the shared socioeconomic pathways, or SSPs for short, are different emission scenarios. So different mix of coal, oil, renewables going forward. In addition to having a different sort of energy mix in each scenario, they also have socioeconomic implications, which are less important for working group 1 because we really care about how much watts per meter squared forcing is put into the atmosphere. But working group 2 and 3 is also concerned with how do humans respond to climate change. And so these actually have full narratives in it, and they're really interesting. It's kind of fun to read the narrative. So for example, SSP1 is the sustainability path and cooperation, where all countries decide to cut emissions very aggressively and do so immediately. Some of these ones in the middle are really interesting. The SSP3 and SSP4 are regional rivalry and inequality. So SSP 3.7, for example, is like Trump world. So basically there's a rise of authoritarian governments. Everyone's out for themselves. They don't want to cooperate. Some countries like burn a ton of coal. Other countries get more sustainable. Interestingly, SSP5, which has the strongest emissions, assumes that everyone starts to burn a lot of coal, but also that there's a lot of equality, that everyone's lives are improved there's improvement in the standard of living globally, but it's entirely rooted in coal or fossil fuel burning. So it's a world where people cooperate and agree, but they cooperate and agree to burn fossil fuels. So it's just interesting to think about those socioeconomic dimensions. Of course, working group 1, what we really care about is the radiative forcing, because that's what determines, that's what we feed into our climate models. The climate models don't model people and the decisions that they make. So that sort of stuff comes in later. So here's what it looks like in terms of the different energy mix. So in the sustainability sort of trade, we have a strong uptick in renewable energy, biomass, but you can see that there's still sort of a decent use of natural gas, more of a drop off in oil though and coal, versus the middle road scenario, everything just goes up together. And then when we look at, the SSP5, or we really hit up the fossil fuels, you can see coal, which is at the bottom in the gray, is really like the baseline of that increase there. So these correspond to different emission scenarios in terms of the total gigatons of carbon dioxide. This is the rate of carbon dioxide release, so in gigatons for CO2 per year. So not cumulative, but now the rate. And so what you'll see is that actually these lowest scenarios, the 2.6 and the 1.9, actually go negative, which means that they assume that CO2 has been removed from the atmosphere and put back into the ground. So that's a negative emission trajectory. It assumes that we have technologies to essentially carbon capture and storage, mainly take CO2 out and actually go net negative. Whereas SSP245 doesn't assume any net negative emissions, but just assumes that we kind of like slowly decline our rate of CO2 emissions. And these others are increasing. These numbers correspond to watts per meter squared forcing in the atmosphere related to the emission of greenhouse gases, so CO2, N2O, and methane. So those are our past, and this is what is fed into the climate models to produce the future climate scenarios. So the first order is, what do these different scenarios sort of play out to in terms of temperature change, right? Global temperature change. So this is a figure not from the IPCC, but from my colleague Ben Cook, but I like it because it shows really nicely how those different scenarios translate to global temperature change, and it also shows some uncertainties. So the green is 2.6, which is one of the more sustainable things. And then we kind of go up as we go up in sort of color here, we go up to the higher emissions. So you can see that the more aggressive scenarios in terms of cutting emissions would basically leave us at around 2 degrees Celsius by 2100. The middle of the road is 3. And then if we go up to the orange and the red, we're talking about anywhere from 5 up to 7 degrees Celsius of global warming by 2100. Now the uncertainty, you can see there's scatter on the left-hand box plot here, is related to each individual model's climate sensitivity. So that parameter that I talked about before. Some models are more sensitive to CO2 change than others. Some of them have an ECS of 5, some of them have an ECS of 2 within that range that we talked about. So the ones that have an ECS of 2 might only simulate, let's say for SSP7, like 3.5 or 4 degrees of warming, whereas the ones with a high ECS would simulate more like 5.5. So that's why there's like kind of this spread and this scatter in these graphs. Because we don't know exactly what ECS is, and as a geologist, I can tell you it's also state dependent and tends to change across warm and cold climates. One way that the report is kind of normalized for that is to present things instead in terms of global warming levels. So basically, what does the world look like at 1.5 degrees? What does it look like at 2? What does it look like at 4? So in this figure from the summary, the SPM, you can see that these are the standard maps of the spatial pattern of temperature change, 1.5, 2, and 4. So, and then precipitation, and this is in percent change, 1.5, 2, and 4. And what this does is it allows you to use both high ECS and low ECS models, since you're just plotting the point at which the model suggests that the global temperature change has reached 2 or 4 or something like that. I think it's also very useful to communicate to the public to present it this way. as just like, okay, this is what the world looks like with this many degrees of global warming, rather than saying SSP this or that. One thing that's new for the report this time that's really cool, and I encourage you to check out, is an interactive atlas. So the atlas chapter traditionally was literally a chapter of a bunch of maps. But now, of course, you know, digital age, why do that when you can just have an interactive atlas online? And so if you just Google IPCC interactive atlas, you'll bring it up. You can explore different future scenarios. This paleoclimate is on here, the mid-Holocene and the last glacial maximum climate simulations are here. You can look at temperature, precipitation. The world's divided up into these regions, the IPCC regions, which form those little hexagons. You can click and look at a time series for a particular region. It's really cool. So this is a really cool thing they did this time that I really like and allows you to engage with the different future scenarios. Okay. So with the remaining time, I just want to go over some of the key messages from the report. Obviously, with 2,000 pages, it's not possible to, you know, distill everything that's in there. There's a lot in there. So I'm going to focus on the big messages that are also headlined in the summary for policymakers and also seem to have been picked up a lot by the media as of late. Some of them are kind of obvious. Some of them are new and surprising. All right, so recent changes in the climate are widespread, rapid, intensifying, and unprecedented in thousands of years. So that last clause in particular makes me happy because that means that we're comparing to the geological record to inform this headline statement. That really the changes in climate we've seen are totally out of the norm. And there's many ways that we can represent that graphically. We can show Al Gore-like plots of CO2 and methane. What's in the summary for policymakers is temperature record for the last 2,000 years, as sort of one piece of context for the trajectory that we're on now. So you see that on your left-hand side here, that the reconstructed temperature, this is the version from the pages, 2K effort, versus the observed change, and you can see how rapidly temperature has gone up. Warming is unprecedented in at least 2,000 years. Possibly warming is unprecedented in more than 100,000 years, is the assessment in the report. And then I love these graphs on this side here. This is basically a detection attribution graph where if you run climate models with just natural variability, only solar volcanic sort of changes, you get the green line. This is 1850 to 2020. Once you add in human emissions, you can see that since 1960, humans basically account for all of the global warming, all of it. And so this is how we know, there's no question, absolutely, the warming is caused by humans, and it's unusual in the context of even that this is for us a short geological record. But and just to plug our own work, my postdoc Matt, who's sitting over here, has a paper that will be coming out soon where we actually demonstrate that the current warming is for sure unprecedented in the last 24,000 years. There was still some uncertainty about whether any time in the Holocene was warmer than present day. Our reconstruction says that there's very little probability that any time in fact, above 99%, 99.9 bound, the current decade is above the 99.9th bound of our reconstruction for the last 24,000 years. So, so stay tuned. This is going to be coming up in Nature, hopefully in the next few weeks or months. I don't know. So, all right. It is indisputable that human activities are causing climate change, making extreme events, including heat waves, heavy rainfall, and droughts, more frequent and severe. This is a strong statement by the IPCC regarding climate extremes. So now we're talking about floods, we're talking about droughts, we're talking about all the heat waves. We can now, this is a big change since the last assessment report, we can assign confidence that these extreme events have a fingerprint of humans on them. Two things have led to that improvement in confidence. One is, unfortunately, climate change has gotten a lot worse since 2013. We're seeing more and more extreme events that are just entirely outside the realm of natural variability. But second, the science of detection and attribution has really improved. and grown. And so there's way more studies that are looking probabilistically, can we attribute this particular extreme event, particular drought, to humans or not, or what percentage of it was made more extreme by humans. And so with heat waves, there's absolutely no question that heat waves that we're seeing are driven by human-caused climate change. The IPCC says it is the main driver. Human-caused climate change is the main driver for more frequent and intense heat waves. And so you see all these red hexagons. These are all places where there's been an increase in hot extremes. You see a lot of triple dots, a lot of strong confidence that this can be attributed to human-caused climate change. So the heat wave, for example, the heat wave that Pacific Northwest and Canada experienced earlier this summer, there was an attribution study that got released right after that found it would have been virtually impossible without human-caused climate change. This is such an outside of the tails, in the natural, in the sort of pre-industrial world, that there's absolutely no way this would have ever occurred without human-caused climate change. So it's really cool. Drought, you can see, less filled in hexagons because there's a lot of, things that go into drought. Drought is caused by, of course, lack of precipitation, but also higher temperatures is a big factor in driving drought, especially in semi-arid regions like here in the Mediterranean. But we do see the strongest confidence of human influence is here in the Western North America, in the Southwest, and in the Mediterranean, where these guys put 2 dots, but we put 3 in chapter 8, and we feel like there's very strong evidence for human-caused drought in these regions. And so largely due, by the way, to rising temperatures and the impact that has on soil moisture, the fact that a warmer atmosphere is thirstier. And so it will evaporate more water off of the soils. And even if your precipitation decline is just kind of moderate, it turns into a worse drought in a warmer world. And that's a phenomenon we call hot drought, which is discussed quite a lot in the report. Here's just an example of a paleoclimate related attribution study, if you will, done by Dan Griffin and Kevin, who's my husband, who works over in the Tierney lab in geography. And they found that using the triggering record of past drought and separately precipitation, that the 2012-2014 California drought was one of the worst in 12,000 years. So you can see the distribution of droughts in the last 12,000 years. 2014 is falling right out on the tail, extremely unusual. Other studies that followed up here also found that there was a clear human fingerprint on this drought that accounted for about 25% of the severity of this drought could be directly linked to human emissions. So as an example, the kind of studies that go into the assessment that we have of drought. Fires. Fires, definitely. So it's not talked about too much in the IPCC report, but I wanted to bring it up because obviously we've seen insane fire activity in California. And it turns out that since 1972, California has experienced an 8-fold increase in summer forest fire extent. And it is linked to human-caused warming and drying. Basically, a warmer, drier atmosphere is making things catch on fire much more. So the Calder fire was sort of the latest one to raise Lake Tahoe, but Cal Fire put out this diagram, I don't know, a week ago that I thought was just really arresting because it tells you what 8-fold increase really means. So from 1932 to 1999, that's that gray thing, that tiny slice. Those are the bad wildfires that happened. And then from the aughts to the next 20 years accounts for about, I don't know, a third of the wheel. And the last 2 years account for over half of the wheel. And so you can see that rapid amp up in summer wildfire extent. And I mean, there's issues with forest management and things like that, but it's definitely studies that have looked at this into detail have found that it really can be linked to warmer, drier temperatures. So I think this change in messaging on extremes from the last report to this one is huge. This is the kind of thing that you can connect with people about because everyone has felt an extreme. This summer, we had every single one. We had floods in Tennessee. We had hurricane. We had fire. We had heat wave. We had drought. And of course, going forward, extremes become more frequent and intense. With every additional increment of global warming, it just scales. And so these diagrams from the summary for policymakers basically are showing you that an event that is 1 in 50 year sort of event in the pre-industrial climate, if you go up to 4 degrees, it'll occur 90, almost 90, be more likely to occur by 40 times. So an incredible increase in the likelihood of extreme events. Another pretty impactful statement, there's no going back from some changes in the climate system. However, some changes could be slowed and others could be stopped by limiting warming. So with regards to extremes, because they have to do with the atmosphere, you can stop them if you stop the warming, and the atmosphere responds instantaneously. The cryosphere and the ocean, not so much. And so when we talk about there's no going back, we're talking mostly about cryosphere and sea level changes. So the projections for Arctic sea ice, for example, what you can see is that obviously things are worse with those red scenarios, those high emission scenarios, but even under the low emission scenarios, we're still facing a world where the Arctic sea ice cover is just going to be lower than pre-industrial. We won't go back. Similarly, sea level rise. Under the lowest emission scenarios, we expect to see 0.5 meter of sea level rise by 2100. That's this much. So maybe that doesn't mean much to us here, but if you're in Florida, it's a problem, right? It already is. Now that's better than 1 meter, or you see the low likelihood, high impact dotted line here, a scary scenario where ice sheets collapse faster than we think they're going to. So it still means that mitigation is important, but we can't go back to the pre-industrial state because these are, for humans at least, an irreversible climate change. But like I said, we can stop some of the stuff that's happening in the atmosphere. Unless there are immediate, rapid, and large-scale reductions in greenhouse gas emissions, limiting warming to 1.5 degrees will be beyond reach, which means we got to do stuff now, right? So, you know, time is running out to keep warming under 1.5 degrees. That is very difficult to achieve. The current commitments do not ensure that. So if we want to hit that target, which has been put forward as a target, as a safe space, then you really got to get mobilizing. And, you know, the special report on 1.5 said much of the same, but, you know, it's, the IPCC is fundamentally a conservative organization because you have to get scientists and governments from all over the world to agree on these messages. So I was actually surprised when these headline messages came out, how strong they were. They were stronger than even I expected. Good news is where we end up depends entirely on where we emit. And like I said, a lot of the worst outcomes of climate change, especially the extremes, anything to do with the atmosphere, can be stopped and even walked back a little bit under the low emission scenarios. So these are trajectories in CO2 space, just to give you a sense of what it looks like in terms of the concentration, the atmospheric concentration. The low emissions have us basically holding below 450 parts per million of CO2 and maybe coming back down towards the end of the century. Whereas the high emissions take us up to, you know, 800 and, you know, as high as 1,000 ppm of CO2. It's very high. Current commitments, some good news, are putting us on essentially the yellow line, the middle of the red scenario. So we are not currently on the red track. That's good news, right? We would like to be on the cool color tracks, but at least we're not on the red track. Here's another visualization of that, showing with the gigaton C per year. The current policies, which are in light blue here, basically would have us at about 3 degrees global warming by 2100, which is not great, right? We still see big changes in extremes and things, but at least we're not on those scary red trajectories right now. And then, you know, to bring it down to 1.5, right, you have to get all the way down here. So that definitely requires strong commitment from the international community to drop this back down closer to the green and maybe the yellow trajectories. So, but a lot of people think we're on like the highest one. And so I just mentioned this to say we're not, we're in the middle zone. So I see that as a positive for sure. Yeah. So obviously my plan to go for half an hour didn't really work. And instead I went for 45 minutes, which is not surprising whatsoever. I just want to say that, you know, where we end up really matters. I already made this point. It matters for extremes. It also matters for things like ocean acidification. There's a big difference in these trajectories in the acidity of the oceans. So you can see that the low emissions basically keep us where we are today, which is still not great, you know, okay, but you don't want to be here because that exceeds the level of acidification during the PTM. So, which shocked me actually, that we could do that by 2100. So don't do that, right? But I think this is one of the things where it really makes a big difference which path we choose. So I want to end by talking about what you can do, because I always get this question, you know, what can you do? It seems the message of the IPCC report is dire. The UN, it was a UN official, not the IPCC, who labeled it a code red for humanity. That was not an official, you know, IPCC thing, but it is a very dire message. It means, you know, we got to do stuff, right? So we got to do stuff. So what can you do as an individual? And these two things are probably the most, you know, you may not think of them, but they're the most important things that you can do. One is to talk to people and meet them where they are. So actually the tide is turning in the US. A lot more people think that climate change is a problem, even if they're on the conservative side of the political spectrum, because they've seen something happen to them, usually an extreme weather event, that sort of turned them around. And they're like, oh shit, you know, something's happening, right? So meet them where they are. I guarantee you global warming has affected everyone in some sort of way. And secondly, you know, voting. We have to use our political system to get policies and politicians in office who are committed to finding solutions. And I want to emphasize local and state, because they can get a lot done, local and state. And thinking about Arizona in particular, you know, we have a very conservative state legislator who's not very interested in this, but, you know, participating in state elections is really important if we want to turn that around and get climate savvy people in charge. You know, people ask me about things like, should I be vegetarian? Should I not drive my car? Should I fly less? Like, and here's what I say, you want to do that stuff? That's great. But you have to be realistic. That does not affect emissions, period. None of that stuff will change the emissions. The emissions are coming from our industry. Our entire society is built on fossil fuels. And in fact, airline flights are only 4% of global emissions, and that's including industrial airline flights. So you can say that passenger airlines are, of course, they're very dirty, but it's only 4%. We learned during COVID, when everyone was grounded and not flying, that it didn't make any difference. Tiny bite, emissions just kept going up. So that's not the solution. It's great if you want to do that and feel better, but you know, the other part of the issue there is that not everyone can do those things, right? If you're a subsistence fisherman, you're not going to be a vegetarian, right? So it's very, you know, can be very dicey in certain cultures and different, you know, people to talk about lifestyle changes. Really, climate change is a systemic problem because, as I said, our whole society is built on fossil fuels, which means it needs a collective and deep solution, way harder, admittedly, but I don't think it's impossible. All right, so with that, I'd be happy to take your questions.
So Jess, if you could just repeat the question from the crowd here for the Zoom audience, and then I will just ask the Zoom questions from here.
Great.
So you can answer that.
Yeah.
Let's take a couple questions from the audience here first.
Andy.
So is it intentional that the other two reports are coming out after the first report? Or is that just in the past, have they come out in the same order, or is that planned, or is that just a coincidence?
Yeah, so the question from Andy is it intentional that the working group 2 and 3 reports come out later? And is that normal? And the answer is yes, they have typically been released after working group 1. And I think it's mostly just logistics, because they do rely on the working group 1 results and assessments to build those separate things. So there's some element of like they need to come after. On the other hand, there are many people who feel like it would be better if they were released at least somewhat closer together, because of course people's first question is, what are we going to do about it? And that's really addressed in these other reports. So the staggering is normal, but I mean, maybe not ideal, but yeah, they're on completely, you have these huge groups of people, all these coordinations, what used to be in-person meetings, author meetings, and now is mostly conducted on Zoom. And so, yeah.
Are you saying the paleoclimate estimates of this report are folded into the whole report as opposed to being one chapter? I'm wondering how that's working insofar as if there's still a group that is responsible for sort of like those paleoclimate things that are then liaising, or does each individual subsector have their own paleoclimate experts for?
Yeah, so the question is, the paleoclimate is disseminated across the chapters, but were there still kind of paleoclimate experts who, were kind of in charge of that information and coordinated? And yes to that. So the paleoclimatologists took it upon ourselves to maintain a sort of cross-working group and help each other, both checking the kind of assessments that we were writing into our chapter and also helping. So, I helped with, there's a box in, I think it's chapter 2 or 3, I can't remember, about the Pliocene. So I helped co-write that. In many cases, there was only one paleoclimate person in the author team on the chapter. So relying on that cross group energy really helps to make sure that things were represented. So yeah. And I think that worked out really well, actually. I think, we were able to make sure that the sort of major things kind of popped up here and there.
Okay, I've got a question from the chat. Ray Leonard asks, so Ray says, if we cut coal production, we reduce aerosols that unfortunately increase temperatures. That is why we hit 1.5 degrees C by 2030, no matter what, and probably why 2 degrees by 2050 is unavoidable. Is this not correct? What do you think about this?
Well, I mean, if we cut coal, that's the first thing that has to happen. And yes, I mean, I think to avoid the higher global warming levels, you also need to cut other fossil fuels, including oil and gas. And so, so I guess, I don't know what exactly the question is, but just to say that if you want to hold to these lower global warming levels, then that assumes cuts not just in coal, but also deep cuts in oil and natural gas.
Other questions here?
Yeah.
You mentioned the conservative nature of sort of the, I guess, statements that the report makes. Were there any instances in this report or past ones where perhaps national priorities or, I don't know, maybe political lines on certain issues perhaps limited what either you or some other authors wanted the reports to say?
Yeah, so I think amongst the scientists, we don't.
Yeah, sorry, could you repeat the question?
Yeah. Oh, sorry. Okay. So the question is, basically, are there ever times when, maybe political interests from different countries, for example, might influence the sort of headline statements that kind of end up being released at the end, and where that might go against, for example, what the scientists were saying in the report. So the report is written by scientists, and so there's not a lot of like political heat, directly into the core of the report, but the summary for policymakers needs to be approved by governments line for line. So where you see that potentially exercise itself is in the summary for policymakers, and they very rarely change it so that it still matches. It has to match basically what the full report is. You can't really change the meaning that much. You do see sort of small changes in phrasing potentially. So if one country decides, for example, like, I don't know, that they don't want, I don't know, they have some reason why they, don't want to highlight something happening in their country, right? They might like change the phrasing of how that's expressed, but not usually the underlying meaning. So, and we don't have any, we don't have any pressure on our backs to do what our governments say, at least, in the US. So.
Okay, we've got a fairly involved question from Grace. And so Grace asks, can you speak a bit more about the experience of participating in such a large working group A? And to add context to this question, were there many power struggles, personal dynamics, or were people generally good at setting aside their baggage? And you don't need to repeat that because it's on the chat.
Okay, yeah, that's a great question. Yeah, this report's written by people, so there's definitely baggage, there's definitely power plays, there's definitely implicit and explicit bias, racism, sexism, countryism. First, whether your first language is English, it's all on the table for people. Yeah, so unfortunately, not like everything, it's not immune from that. So sometimes disagreements are scientific and they're based on you've got one camp, and you really have it in the literature. There's like one camp on something that's like it's this, and there's another camp that's like it's this. And you're like trying to figure out, okay, like what do we do? How do we assess this really contentious issue? That's a scientific side of disagreement, but there is also a lot of personal issues too. And I think that there was some, negative press after the first author meeting about some, basically people treating others, not well, not treating women well, not treating people from, non-developed nations very well. And so the IPCC did institute some DEI training, which I thought was a positive step and towards an improvement. But yeah, it's not easy and it's very stressful. And people get stressed out because there are tight deadlines. So there's definitely a lot of conflict, I would say. Yeah.
Did you do it again?
The question is, would I do it again? Probably not. Probably not. I would say that I would have said absolutely
impossible.
Yeah, I would say it's very unlikely. Very unlikely. I would have said virtually impossible before the report came out. I was excited to see the public engagement with the report and excited to communicate that. And so that's the only reason why I'm not saying absolutely not. But it's a huge commitment and it is extremely stressful. So I'm not sure I would do it again.
Okay, we've got another question from Diane Thompson in chat. So Diane says, I also wonder how the contributing author list works. How much input do you give in order to be listed here? Is there a way to express interest in contributing? Or is it really up to the lead authors to reach out / get folks involved?
Yeah. Yeah, so traditionally it is up to the lead authors to reach out to people that they think could help. And so there isn't currently, or at least not in this round, was a mechanism for people to volunteer. And you can imagine that that is potentially like a biased pathway. And so maybe, something that the IPCC could do moving forward is to create, a system for people to potentially express interest. Because obviously people are going to go to people that they know and they know their work and that they're like, okay, I need your help, so I definitely did it with drought. I went and asked Ben Cook and Park Williams and some of the other people that I know are doing work on drought and, that I'm familiar with their stuff. So yeah, so that's the way it's been done. But I take the point that that's not necessarily the best way to do it. So that's a really good point.
Yeah, other questions here?
Yeah.
So kind of related to would you do it again? It seems like a tremendous amount of work that goes into it, and these have been coming out since what, the 80s?
Yeah.
Is there a demonstrated impact of these, or are we just, documenting in excruciating detail how the ship is sinking and then continuing?
Yeah, I think so. The question is, we've been doing this since the 80s, and ultimately the ship is sinking. So, do these reports have an impact, or are we just kind of wasting our time, essentially, like writing over detail? I have really two feelings. I mean, I'll speak this personally. Like, I also share that concern that spending time documenting things in excruciating detail may not be the best use of my time. I'd love to see the IPCC move to shorter reports, more regional, really focused, like this is our South American report, and we're just gonna like go for it and things like that, rather than this huge 2,000-page thing that people won't necessarily read. I will say that the headline messages that came out of this report this time were really important and definitely got people's attention, hence impact. So, you know, whether that translates, obviously, what governments choose to do or not do is their own prerogative, and they may read this report and be like, yeah, that's great, but I'm not going to do anything, you know, screw it. But I mean, I was surprised by, I think with the narrative on extremes in particular, there was a lot more coverage in the US, especially given our extremes this summer. So awareness, public awareness is one positive impact. I attended a briefing with Congress a few weeks ago. I'm doing another one next week. And so Congress is taking note. You know, the Biden administration says it's a priority. You know, what they do, we'll see. But, you know, I mean, you can say a lot of things, doing things is different. But I'm pleased to see the engagement. So I think there is an impact. And so there is some element of, I think there is a purpose to these reports. I agree with you that I'm not sure we need to be writing 2,000-page long assessments anymore. I also think that a lot of modeling resources are spent on running those projections, possibly too much, in my opinion. Speaking as someone who wants to do paleoclimate modeling, there's limited resources on those supercomputers, and they spend all of their time, a lot of these groups, NCAR and GFDL, spend a lot of resources running these CMIP runs, and maybe we don't need to run all of them, you know, or whatever. So I would like to see the process evolve. But I still think that reports on some level, even if maybe more succinct ones, maybe national or regional ones, are important.
Okay, Jess, I'm gonna be a little selfish here and ask you a question myself. So, you know, I found it a very interesting message that we've avoided kind of the super high SST 8.5, and you know that's an important thing, especially considering how RCP 8.5 has been, you know, taken into consideration. But so my question is, what kind of talk in the IPCC talks about the potential impacts of, say, tipping points, even along the lower pathways? You know, some irreversible, abrupt climate change, even on those median pathways. Can you just talk a little bit about that?
Yeah, so the question is, it's good news we're not on the highest emissions, but you know, what about tipping points, abrupt changes, or unexpected sort of shifts in the climate system that could happen really fast and be damaging? Yeah, so those are those low likelihood, high impact storylines I was talking about, and it was very clear in the report that we needed to talk about those, even if we consider them unlikely. So one of them is AMOT collapse, right? Now, in models, a lot of these tipping points are not crossed until you really hit them with a lot of CO2, which is why we typically talk about them in the narrative of high emission scenarios. That doesn't rule out the fact that they could happen on lower emissions, though, because especially when it comes to things about the cryosphere, you know, there's a lot of debate about how fast, you know, ice can disintegrate, and that's an evolving field. And so, you know, some of these middle road scenarios still have us at 600 parts per million at 2100, which is high, right? So we're talking about close to EO boundary levels. So you have to ask yourself, like, where are those tipping points, especially when we're talking about cryosphere? So some of the tipping points that are discussed are ice shelf collapse, AMOT collapse, permafrost, but that's largely believed to be not, you know, it's, we talked about in your talk that that's not so much. Amazon dieback is one that I wrote about, which is actually terrifyingly not outside the realm of possibility, because it's one of those where it depends on climate change, but also land use. So when you start bringing in what people are going to do, are they going to cut down more of the forest? And because it's a bifurcation based on those two things, that actually scared me working on that one. Other changes in the land surface and feedbacks into the climate system. We also talked about geoengineering, specifically sulfate aerosol injection. both starting it and ending it, and termination shock. And so this is, one of those tech fixes to global warming. Basically, it's you shoot sulfate aerosols into the stratosphere, essentially simulating what happens during a large volcanic eruption. The sulfate aerosols block out the sun. And for a volcanic eruption, that would typically just cool the climate for a few years. Of course, if you kept shooting them up into the stratosphere, you could cool the climate long term. The problem with it is, of course, once you start, you can't stop. The minute you stop, you just go right back to where you were, right? It doesn't help ocean acidification in any way, obviously. And if you do stop, termination shock can cause really abrupt climate changes potentially in different regions. There are huge impacts on the hydrological cycle by messing with the top of the atmosphere radiation balance. So unsurprisingly, it's not recommended by anyone I know, at least in the IPCC, as a solution to climate change, even though it is actually doable and very cheap, but the side effects are too scary, we think. So
Maybe one last question, 2 more.
Yeah, so coming back to what you say, that you wanted us to stop driving over vegetarian, what's your advice to the developing world? Should they just sit back and enjoy them?
well, so I said I'm not giving that advice, right? So you're saying what's my advice? Like,
To the developing world.
yeah, well, I mean, my advice to the developing world is, first of all, a lot of these countries are not responsible for climate change. This is something that has been, the top emitters are, China, United States, Europe. And I do think the responsibility relies on us to, to start and be, to model moving to a better energy base, right? In the developing world, the situation is a lot more complex. It's sort of like what are the things that can be done within the scope locally, right? But I feel like some of the renewable energies, right? Like, if you're lucky enough not to have a country that's entirely based on coal in the first place, maybe you can avoid the fossil fuel phase to some extent, or maybe it's less of a fossil fuel phase and jump to solar renewable. Solar technologies are becoming actually so cheap now that they're starting to be cheaper than even, definitely cheaper than coal, but also starting to rival oil and gas. And so with the dropping cost, I guess I would say to developing nations, consider whether you can jump, to a renewable phase. It may or may not be possible. But I think, I'm not going to tell anyone what to do. I guess is my take, right? It's more like, from my perspective, we need to have political leaders who are going to engage and start organizing things. So if you're going to build a grid that can take solar energy, if you're going to build public transit, build good public transit. So and it's like us in the United States, where we have this messed up grid that's super old and there's no public transit anywhere. We can't take a train anywhere, It's like, man, wish you could travel back to the 1950s and say, dude, yeah, don't do it. But I'm not in the business of telling anyone what to do. I think, we all come to it in our own way, really. And it really depends on, where you're at. So.
All right, let's give Jess another round of applause.